Common problems in illumination design is the determination of radiant or luminous flux on a region of interest, say on a distant screen. I'm going to show you a significant breakthrough in ZEMAX 12 that allows very fast, accurate computation of this flux for an arbitrary optical system without the need to trace millions of rays. This feature, called Reverse Radiance, traces rays backwards from detector to source. The algorithm eliminates the tracing of rays that do not land on the region of interest, greatly speeding up the computation time. Additionally, the actual measured near-field and far-field intensity of the source is used, along with the ray data, to accurately determine the flux. In addition to being extremely fast, Reverse Radiance gives you a simple method of determining if the computation is accurate, as the convergence of the results can be tested. These are two huge advantages Reverse Radiance has over conventional ray tracing. Reverse Radiance is now available exclusively in ZEMAX 12 IE. Let's take a look at Reverse Radiance in action. I have created here a very simple optical system consisting of a source model, a lens, and two small distant screens I am modeling using detector color objects. I have a 1 centimeter squared detector on the axis of the lens, 1,000 millimeters away from the source, and another small detector 300 millimeters off-axis in the y direction. We could use a more complex optical model, but the technique I am going to show here will work for virtually any kind of system that projects light onto a screen or target. For the source model, I will select a TI white light LED radiant source model file as measured with a prometric imaging goniometer equipped with an optional spectrometer to get the full color spectrum of the source. I want to generate a ray set to represent this source. I'll choose the source model name, then select 1 million rays for the ray set. I click on Generate, the ray generation begins and takes just a few seconds to complete. Now back at the editor, I'll load the source file I just generated. I just select the source file name. Note it matches the file we just downloaded. The total power in the file is about 3.9 lumens, so I'll copy and paste that power to the value. Note ZEMAX lets you scale the actual measured power to another value if you have some reason to do that. We can use the Radiant Source Model Viewer to see a picture of the measured source. Note this is a true color image as the source was measured with full spectral data. The Radiant Source Model gives us accurate near-field, far-field, flux, and spectral data. The viewer allows us to view the source from any angle. We can also use this viewer to determine the orientation of the source as it was measured and to get an accurate measure of the size of the source, which will come in handy in just a moment. It looks to be about 2.5 millimeters in radial size. Suppose we are only interested in the total lumens and color on the entire detector. The traditional way of getting our desired flux is to trace rays. Let's trace all these rays and see what the flux is on the two detectors. Tracing 1 million rays on a very fast 12-core machine like this one only takes a few seconds. But of course it would take much longer for a more complicated system. Now, with the ray trace finished, we can see the flux on the detector is about 4 times 10 to the minus 4 lumens on the on-axis target and about 2 times 10 to the minus 4 lumens on the off-axis target. But note that only 135 and 72 rays, respectively, actually hit these two targets. With so few rays on the target, how do we know the results are accurate? The typical answer is to trace more and more rays and see if the result converges. But we may end up tracing tens of millions of rays just to get data for the few that hit these targets. This is the kind of problem at which Reverse Radiance excels. Reverse Radiance traces the rays backwards from detector to source and then determines the proper intensity of the ray once it interacts with the source. Here's the same system set up for a Reverse Radiance analysis. First, I've added a small sphere around the source location. This is the boundary object. The boundary object is a dummy object, and you can use any surface or volume object of any shape you like. All that matters is that it surrounds the source and is not straddling any physical part in the secondary optics. I have made the sphere 4 millimeters in radius based upon the size I observed with the source viewer. Next, I added a Reverse Radiance target object. This is also a sort of dummy object. It is used to guide the rays from the detector towards the source. I have placed 2 of these targets, 1 for each detector. I have selected a size and sampling grid that is enough to ensure rays from the detector will overfill the source. Finally, I added 2 Reverse Radiance detectors. These are very much like the detector color object, except they will launch rays toward the source and use the reverse radiance technology to determine how much flux they collect, rather than wait for rays to hit the detectors. The detectors require me to define the source object, boundary object, and target object. It only takes a minute to set this up correctly. It's easy to see if the target is set up correctly because I can choose a ray color and ZEMAX will draw the reverse rays on the layout plots, as you can see here. Now I invoke the reverse radiance analysis feature. I can select my detector and ZEMAX launches the rays and integrates the light from the source. Note ZEMAX determines the power on the detector, the radiant or luminous intensity, and the tristimulus color as well. Note we only traced a few dozen rays here, not millions of rays. One of the best features of reverse radiance is that we can easily increase the sampling grid and see if the results are converged. Once the results converge, we know we have an accurate measure of the flux. Note that unlike equal amplitude ray tracing, the accuracy of the results does not depend upon the magnitude of the flux. This makes reverse radiance ideal for accurately determining things like contrast or light levels in primarily dark areas of the lit scene. Reverse radiance works best for detectors that would otherwise gather few rays or very low flux, and for systems that do not form images of the source, such as critical illumination systems, and for radiant source models that do not have a lot of very fine structure in the near field. Reverse radiance is just one of the breakthrough features of ZEMAX 12. I hope you find it a very useful and powerful tool for your design and analysis needs.